We're now in the last part of this presentation that was given to Nkosi, which I'm repeating here for you. Now, the last part is what can be done now to leverage general purpose large language models and MBSE to tackle the left side of the V. And again, I'm just going to revisit something we covered in an earlier slide, that we are looking for a problem, looking for a solution for the scalable problem of communications. We want to eliminate some of the documentation that's going back and forth, and we want to replace that with essentially a single source of information that we can put information in and then retrieve it out in the format that we want. And we want to kind of get to this solution, and we want to be able to do this in a way that basically is scalable and can be done for an organization for that. Now, the issue that we had basically could be set down into these main problems that I was seeing with trying to accomplish this now. First, how do I reduce the number of tokens required? That's the first thing. As we mentioned in the SysML V2 generated content, the number of tokens was an issue. I was using a very small model, and I had to get it down to an element of the logical architecture. I was running out of tokens. Now, I can sit around again and wait for the large language models to be able to have more token, but that's not what I want to do. I want to do something now. And now, at this point in time, was about in the December timeframe of 2024. Actually, I was on break and I was looking at this, and I was, it was keeping me up at night trying to figure out, well, how can I use AI now with my MBSE? Now, the next thing I wanted to do is I wanted to make sure I could have good performance. How can I improve the performance? At that point in time, 4.0 wasn't very good at uncomprehending SysML V2. I actually had multiple discussions with it, with ChatGPT about what would work, and actually it came out saying that a YAML or a JSON file might be better, because essentially when you're processing SysML V2, it essentially has to take the library and then create a semantic representation of the model from the content in the library to get to that domain level. That whole process takes a lot of effort, but also just the sheer number of tokens that go into basically providing both the data for the ARCADIA library and providing the data for the model itself consumes a lot of tokens. So that's kind of why. And so, the kind of recommendation was if you could reduce it down to what is actually the semantic representation of the model. Essentially, if I could work on something that had already been reduced, it will improve the size and the performance, because now I'm getting to a much smaller set of the information. And in this case, performance, at the December timeframe of 2024 wasn't that good at even understanding, what a component was, a functional chain. That has improved dramatically. So kind of the pressure falls more back down onto the first problem of the number of tokens. The last one is an interesting one, is that we want the domain language to speak the language of the systems engineer. And that's kind of why I'm sticking with I'm using the ARCADIA library. The ARCADIA library is a higher level language. It has terms like components. It doesn't have terms like parts. It actually talks about allocated functions to components, and instead of saying relations, it's not being specific relations. So I'm actually speaking in a different language with AI. I'm actually elevating the language to be the language of the systems engineer. Any systems engineer will want that to be the case. Also, any downstream engineer would also want to have it in a language that is at least at that higher level. So this is the other part, is that we got to get the large language model to speak that language of the domain engineer. So that's why I really can't leave ARCADIA out of it, because that gives me that language of the large language model. And so I was looking for solutions then, solution approaches. And one of the things I did want to have is this system engineering understanding. So I took these problems and put them into then a Pew analysis of it, and looked at what we could do. And I've basically using SysML V2 kind of was where I started from, as kind of the baseline. And when I was looking at this, one of the things that did kind of highlight And I couldn't do any of these things very well with SysML V1, mainly because I don't have a semantic, I don't have the ability to subset out. Basically, I would only have something way to subset out by using diagrams, essentially, the content. There is no really APIs to get at, no consistent set of APIs to get at the SysML V1 representation. The static representation of the model to be easily understood. Diagrams are really the only consistent representation there is, and we saw that we could do stuff with that. We could use profiles also on top of the diagram, but again, that would mean I'd have to install the profiles, and I'm still just working with diagrams. I'm not working on the actual model content. One thing that with Capella and ARCADIA, there is a rich set of semantic-aware APIs for ARCADIA, and that really comes from this GitHub site that's supported by the InfraGo organization, and they have published a number of times in Capella Day on some of the things they're doing. It's a very rich set of APIs that are semantic-aware, so I can go in and ask for things like diagrams, I can go in and look at components, I can pull out functional chains. So it is a semantic-aware API that I could then use as a way to pull content out of the model and essentially make a representation of it. And so that's what I did. I started this process of building a set of tools that basically allows me to do these three problems, to address them. And essentially this is the end result. Basically, we use a Jupyter Notebook type of environment. In this case, I'm using SimCenter Studio, but again, Jupyter Lab could be used for that, where I basically go in, I identify the project for analysis. I prompt, in many cases, for model content to be used for analysis. And that prompt is, again, using some capabilities around creating embeddings and using a vector approach to locate the content for analysis very quickly. And the content I look for is diagrams, or I look for model objects by phase, so I actually can search by phase and by model content using this prompt. Next, I create a structured content based on that model content, and the structured content format I'm using is YAML. It is a recommendation from ChatGTP that it was a good format for it to be able to comprehend easily. And essentially, I'm making a semantic representation. I'm using the semantic representation of the model and creating this YAML representation of it based on the direction from the prompts. I usually display the content using just standard APIs for displaying the content in some format. If it's a diagram or an interface, I can display that with some libraries, contents from, again, the InfraGo organization. Next, I execute a set of default AI prompts. These are default prompts that I've defined for things like components and functional chains. And then I execute the ability to have follow-on prompts. So I can actually have a set of my own prompts, one after the other, with memory built into the tool. So it actually has memory for the entire notebook session. It doesn't have memory across notebooks, and in some ways that's very good, because then I can pass the notebook on to somebody else, and they can run the notebook and get essentially the same results I got, because it's not building on memory that was saved by me when I ran it. It's basically giving the results based on a fresh content of that's being used. So it's kind of interesting. I've looked at incorporating memory in different ways, but in this case, I just have memory for as long as the notebook runs. So it means you could go add more cells, add more prompts, and just keep building a chain of commands and do all kinds of things that way. The next thing is I actually have an interactive chat mode, so you can get into an interactive chat, again, using all the information from the previous session. And each time I do interaction with it, I do actually list the number of how many tokens have been consumed, so I can actually kind of get a view of that. The implementation is essentially like this. It uses you put in you run the notebook. It creates embeddings if they're not created based on the information that's in the ARCADIA Capella model. These embeddings then are used so that I can do very quick retrieval when I have a request for analyzing, let's say, a diagram or a component object. Once that request is fulfilled and the object is found, I create basically a structured content, again, from the system, the system model. The structured content is this YAML representation, which is yet another markup language. It's a very readable notation. Also, it's very compact. And so I use that information to pull the information from it. I'm pulling information that I feel will be relevant for doing analysis. And so I'm pulling out things like the descriptions and the related objects that may be relevant to that component. Basically the inputs and the outputs. I pull in the functions of that component and essentially build out a representation of things that you might want to reason on or generate reports on for that particular component. And included with that is any functional chains that the component may participate in. So I'm basically pulling out information. I usually stay within one phase. I don't jump phases of content. You can pick the model in one phase or another. That again limits the number of tokens, so it helps save the processing power. The great thing about it is that, this is a very efficient approach, and, looking at the number of tokens, it's amazing, how low the number of tokens consumed are based on that. And what this has led then is the development of something completely new for a system engineer. What it basically ends up developing is a system engineering knowledge partner. It's essentially an AI entity that you're working with that actually can look at your system model, critique it, help you enhance it, help you analyze it, and verify it. And so all these things can be done because the system engineering model content is now being visible to AI. So one of the things that I've found is that, the deep knowledge of different ARCADIA methodologies means that I can interact with the AI and entity in this way. It's not quite an agent, but I can use that term agent. I can work with the agent to basically give me suggestions of improvements. It can be a peer of an invention, so I can use it to help me do domain analysis. It can actually pull out example architectures and define what the example architectures might be. And it can be an assistant in analysis. It can basically use ability to pull reports out of the model. It can even generate code from the model, and I'll show some examples of some of this as I'm working through it, and in future videos we can look and dive into that. It can be also a peer and communicating downstream. Again, AI is very good at translating terminology, and so if I want to translate from a term of ARCADIA to a term in another domain, it can help. I can define a prompt that will do that, and it will be able to help translate from one terminology to the other. And it's also, of course, a peer in verifying the models, and also a peer in writing requirements. It can do a very good job writing requirements. So essentially, it can it can help with requirements analysis. And this is really the left side of the V problem, where you're doing requirements analysis, you're developing your architecture, you're analyzing and verifying your system as you're doing it. And this left side of the V, and sometimes I've heard this term called a mini V because it is kind of a V shape, basically can be applied against whether you're working in a waterfall model, a development process, an incremental or spiral model, or if you're doing more of an evolutionary approach such as an agile development. There's always a left side of the V problem that you're working in. And this knowledge partner can be very helpful in all those phases for it. Now, how this is working, this is a graphic here of essentially how it works and how this problem has essentially been solved at this point, is that we use Git as kind of the information hub for the information, for the model content. And we're basically using Capella as the Capella or SMW, System Modeling Workbench, as a Siemens product. We're actually using that to capture the architecture. We are using tools that allow us to bring in requirements, also into this architectural representation. In this case, I have examples with using Polarian, and I have examples with team-centered requirements. I can bring that representation into the model, and essentially then I'm able to use the Jupyter Lab tools to bring AI in to help with the analysis and verification. Likewise, I can even use the analysis and verification tools to generate content to help populate requirements. And so I'm going to walk through now a couple of examples of where this is used. And I'm going to use the bike example that we introduced in the very first video of this series to do that. So anyway, this is kind of, and then of course, since I'm using a notebook environment here, that same notebook could be provided to anyone else downstream who wants to get the information from the model also, because we're using a centralized source for that, and that's basically being Git. Okay, so now the first thing we're going to do is we're going to do a little bit of demonstration around using this knowledge partner in a system that is basically a mountain bike with a subsystem that is a braking system. And in this case, the braking system using the functionalities of Capella is actually a replica being brought back into the model. And so in the earlier video, the first video that we did of this series, I actually was working on the actual braking system model directly. In this video set, I will be using the braking system, but I'm going to be working on a replica of it that's been included back into the model. And the approach that I did use was I took the logical and did a system to subsystem transition to make the braking system. The braking system was then enhanced all the way up to the physical architecture and then brought back in as a replica. But this, and again, this is all kind of using this mini V of requirements, architecture, and verification. So an example of what we can do, and again, these are actual prompts that were put into the notebook and the results that came out of them. First one is what would be the operational capabilities associated with a mountain bike. And so in this case, the prompt came back with, this is again not using the model as reference. It's actually just creating this content and giving me the results back. And in this case, what I did is I actually then turn those into diagrams. So in this case, I'm using the knowledge partner as a peer in invention. It actually is helping me create the actual operational capabilities of this mountain bike and capture them. And then I took them and actually turned them into functional chains or operational processes. In this case, they are operational processes, and depicted them by the different colors. So each operational capability, as per other training I've done in the past, the terrain navigation is represented by a corresponding functional chain for the terrain navigation. And so each one of these are linked, and you will see a report in a minute or so that actually shows how they're related to the actual operational processes. The next thing I did was review each operational capability and verify that we have the appropriate operational process. Now, in this, to do this, I actually fed it the diagram of the operational capability diagrams. And this is an instance where when I pull in the operational capabilities from the diagram, I actually follow the relationships to the operational processes. And so in this instance, we get a report then that looks like this, where it actually shows what the related operational processes were to the operational capabilities, and basically states whether it verifies that I've captured everything completely. So it actually is doing a verification in the prompt. So I said, terrain navigation, these are the related operational processes. Over here in mountain trail ride, there's only one operational process, and it shows what that one is. But I've again shown how I've implemented each of these operational capabilities, and it's giving me a report. Now, the entire report format is coming from OpenAI. It actually is working on the YAML representation of this model, and that's what's essentially generating the content for it. The next one I'm going to do is I am taking the operational capabilities and I've turned them now into capabilities. So I did a transition to do this. I did the transition. I also then created the operational analysis, the system analysis diagram for it. And you can see it looks fairly similar. Now in this case, when you get to system analysis, it's time to start thinking about requirements. And so this is again where it can be used as a peer in invention. And in this case, I'm using the system analysis report. I'm actually putting in a prompt, and the prompt is actually generating out the content. Now, I'm going to just jump over, pause for a second here. I'm going to jump over, and we're actually going to see this live then in the tool. I'm going to open up a model, and here's my model that I have. In this case, I'm going to go to the essay. I basically have here a model for system analysis, and I'm actually going to show this be done. So essentially what I'm doing here is I'm going to start with loading up the mountain bike model and its library. So it's loading up both of them. And again, this is using some of the standard tooling from the InfraGo organization and their libraries that they use. So I'm loading up a model. Next thing I'm doing, I'm going to generate embeddings. And again, this is code here that will generate the embeddings that I'm using and actually create a JSON file. And that JSON file will hold those embeddings. That's what I'm going to use to do the query. Now, in this case, I'm not doing an interactive query. I'm actually just saying, go ahead and query and select the top objects. And in this case, I'm telling it to pull out the mountain bike object. So I'm pulling out the SAB mountain bike object. And it's basically then saying that it found it. So it found it, and it found it with a score. Basically, I'm using the cosine approach to find it. Next I do is I generate the structured input file. And here I'm generating the YAML representation. As you can see over here, there's a YAML file that's been created. That YAML representation is then written to the file just for a snapshot. And then I bring that information out, and I do generate some contextual diagrams if they are available. In this case, there's no diagram for a diagram. I'd have to, this is for, works very well for objects. Next thing I do is I basically launch OpenAI. So I'm basically now creating my, my agent or my AI assistant that's going to basically be working, and that's what essentially I'm doing here. And then I give it a prompt. And in this case, the prompt that I'm giving it is to develop some user requirements. And I said, create a set of 20 user requirements for the mountain bike based on the mountain bike trail function. Format the requirements in the following way. Each requirement will have a heading, body, and rationale. The heading should be 5 words, the body, and so this, and provide a rationale for each requirement. And this is essentially the response. Now, what I'm going to do is I'm just going to go ahead and run this so you get an idea of how the performance of something like this would be. Now, again, the embeddings usually do take a little bit. They may take a coffee break to load up the embeddings on a large size model. So it's in this case, the model is fairly small. Right now, it is actually right here. It's getting ready to run the prompt, and the prompt is running, and it takes a couple seconds for OpenAI to respond. But that's actually 10 to 20 seconds for it to respond. And it will come back with the response. So we'll just wait here while the response comes back. And here's the response. So we're seeing the response from OpenAI coming out. So it's basically, here's the requirement. Here's the set of the user requirements. Smooth gear transition, talks about the mountain, but shall provide seamless gear transition, the rationale. And again, this format that it's coming out with might vary slightly from one interaction to the other, but it's basically capturing the information. If I go back to my slides, you'll see that it's slightly different. But this gives you an idea of kind of the input for it. And then down here, I'm launching into this kind of interactive chat. Now, this interactive chat will build upon the information that was in the previous one. So if I say in here, list all the rationales. It will build upon that information that I had in the previous response as it's generating the response for it. And again, I'm using standard OpenAI APIs to do this, and I'm not, and so there's the same information that's responded back from the rationale perspective. Anyway, so going back to kind of the slides on that, and you can see that there is some variation. Here's the slides, and here were the responses that were delivered that particular day when I ran that exact prompt. And so there are some differences. Now, the next thing I was able to do then is actually take this model and basically build out a logical architecture representation of it, and all the different views of the logical architecture, including basically a stopping chain, provide comfort, terrain adjust. Now I'm basically decomposed the functional chains I had around this ride mountain bike. Powering and shifting have been decomposed, and now I have terrain adjust, provide comfort, steering, and handling. All these different things are now decomposed in the logical architecture. And to do, then I can be able to go and turn around and create a prompt for the logical architecture. And in this prompt for the logical architecture, I can actually get into a more, let's say, a more performance-oriented requirement. And when I do that, then, of course, now that I'm building on the logical architecture, it's actually now including the terminology of the systems, because now I'm building around a suspension system, I'm around a braking system. So you can see the AI is helping me write requirements, good, clean requirements in the language of the logical architecture. And so I can use this to help develop, let's say, system requirements, or in this case, system performance requirements. So it's a very powerful tool to help generate the requirements. And again, I can get the requirements, and just again, by modifying the prompt, I can get the requirements into a format that could be easily imported into a requirements management tool, either direct, and it could be imported into by cutting and pasting, or even to the point where I can automate the process, where I can actually get the format into a format. And in this case, sometimes I can create a format that can be converted directly into a Python command that then can be turned around and loaded into a model. Next example, of course, of functional requirements. Very easy to write functional requirements in a similar way. So here's some examples around functional requirements. Now, now it starts getting, now next thing is a much more interesting challenge. What if I was able to actually ask AI to generate a report around impacted components? And in this case, you can do that. So I'll say here, generate a report of impacted components if we were to introduce an electric seat post adjustment. And so it's going to now then use again, the model, the logical architecture model, to kind of generate a report. So it'll actually put together an impact assessment report introducing the seat post. Again, this was a very simple prompt. So I gave it, the ultimate amount of freedom to generate a report. And, the more freedom you give it, the more difference the report might look like from basically one time to another. But in this case, this is what the report actually came out with. It talks about using the existing seat post components and what should be modified, wiring, what functions might be tweaked as you go through it. And then eventually even the impacted functional exchanges. So it gives a pretty detailed, and again, it just comes down to the prompt. The more detailed the prompt, the more detailed report and information you're going to get. Now, continuing with some of the demonstrations here, the next one I did was I took the logical architecture and turned it into a physical architecture. In the very first demo of the series, I showed a video of interacting with a coworker around a mountain bike braking system. That was actually, again, it was in Capella, for you to understand Capella, that was actually a rec that was being used. It was actually the system model of the braking system, which I had decomposed and developed. And then now this is the replica being brought back into the model. And this is the replica showing here of what I'm basically doing the analysis on. It does have functions for every one of these behavior components inside of it. And essentially, I'm going to be asking some questions of the architecture model. In more detail, this is what I'm going to be asking questions around the right hydraulic braking assembly and around this particular interface. Notice the interface has a very cryptic name, PL33, auto-named. We're going to be asking things about that. So in this prompt here, I said, give me a report. In this particular thing, I actually identified a component. So I actually told it go to the hydraulic braking physical assembly, that particular component, and I gave it a prompt to produce an interface control report for that right hydraulic braking assembly. Description of the node component, a report for the physical nodes and respective physical links, including allocated component and functional exchanges, and ports and exchanges, and a table. And the end result was what you're seeing here, where it actually gave me an ICD type of report based on the physical nodes and the links. Now, again, I'm using the terminology of ARCADIA, and that's because the semantic representation that I used using ARCADIA, and also the AI understands the terms of ARCADIA. And so because of those things all kind of connect together with the YAML representation, it's able to basically understand my prompt and basically give me the response back that I expected. And notice it's getting right down to the port numbers. And so that actually shows you very clearly that it's not using information from the world. It's using information from that specific model. And then likewise, I can turn that around. And in this case, I'm basically giving it a prompt to analyze PL33. In this particular one, I actually used the entire diagram for that representation. And I said, denote all functional chains impact. Write a report on the impact of the loss of this interface. Describe what the rider may notice and recommended actions the rider might take in order to get home safe. And then this is the type of report that it generated. Now this gets all the way back to kind of what we saw earlier when we did the demonstration. So it's basically looking at the physical component. It's telling me the functional chain, and you can see that again. It's the rear brakes stopping because that is part of the left side of the left side interface that's being connected, and that connects to the rear braking functional chain. It's telling you what the rider will notice, and that's now not going outside the knowledge that's in the model to general knowledge that OpenAI 4.0 knows. And then also gives actions for the rider, and that's again based on on general knowledge that the AI engine has. So I'm going from basically the model representation very clearly. I'm working on a model object going to outside general knowledge being brought in. And other ways that you can see that this could be used it could be an aid in verification. Again, a prompt like this one here around generating an FMEA could be used as a starting point for generating a failure modes effect analysis, because I could list the components and the functions and then have AI actually give me potential failure modes. So again, it's changing the way that I work with models, because now I have a peer that essentially can see the model as fast as I can create the model and then save it to chat to basically into Git and do the work. Key findings then is that a common domain language, though, is critical for interacting with the AI knowledge partner. This example shows that the ARCADIA domain language becomes a way to communicate with AI. And the question is, with organizations, do you have a language that you use? And do your your tools support it well? I would not want to be interacting with parts or relations. I like being able to say things, well, tell me the functions that are supported by the component. So again, having this higher level language of ARCADIA is a wonderful thing with interacting with the models. The other thing that I found out is that working with these notebooks is very desirable. Being able to actually use a notebook to create the content, as I was showing you, helps you tune your prompts. It allows me to make it very reproducible, so I can give information to somebody else to reduce it. It aligns kind of with some basic principles that you see here that are denoted in the COSI handbook that basically allows you to do it. And it's really very helpful to have the kind of the notebook type of tool, especially as a systems engineer. Before I had the interactive ability to chat with the model, and actually find myself not using it very much. I use the interactive maybe to try something new out, but I always find myself going back to now building the prompts in, executing the notebook with the built prompts. Again, just a minor change sometimes in a prompt can lead to a very different results. So I found myself not really using the interactive capabilities very, very much. Now, can we use this model with, let's say, a standard GPT? Yes, you can, because the YAML representation that I create is portable and can be brought over to another large language model and tested. Also, the embeddings actually only works with that, but a lot of the other tools work. The embeddings don't specifically work, so that would be one thing. But you can skip the embedding step if you know, for instance, what component you want to look at. I'm just using the embeddings to help search things quickly, and it allows me not to look up the UUID of the component. So it's possible to use these tools that I have without using some of the OpenAI capability with them, and then you could use it with your own large language models where it could be adapted to it. Okay, conclusions. Basically, the combination of AI and MBSE will change the way you work. I've found it has dramatically changed the way I work with the system. It helps me, and now I'm working at extending it. I'm able to have it make update to model content. It can update requirements. It can start creating things like verification tests. And it can also be used to translate. So these are the directions that we're going. Again, the key thing to consider is, do you have a domain language you can collaborate over? if you're using Capella, which you probably are if you're on this channel, that is your domain language that you're interacting with, and it's a very powerful one. Now, if you want to go to SysML V2 in the future, I would stay tuned, talk to my peer Kieran Ryan, and we can discuss getting access to the library that we have that uses the terminology of SysML V2 mapped to the ARCADIA language. Now, and where we see this going as an organization, we see the configured instance not just being Git, but it will expand. And this is another direction that I'm going in, is that we're repeating these use cases that I have right now, repeating those use cases on SysML V2 and ensuring that we'll be ready for SysML V2 when it becomes kind of a general standard and format for models, no matter what the source of where the model comes from, whether it's being Capella, System Modeling Workbench, Rhapsody, we'll be able to absorb that format and be able to use it and then do the same analysis and verification requirements capability with a knowledge partner to do that. So, key takeaways from this set of presentations: the promise of SysML V2. It's a lot of has been done. There's still some more support work that needs to be done around this support for domains, and AI might be the solution for that. Large language models combined with system models have huge potential, grounding analysis in the content of the model. And what can be the result of combining the well-formed model? The result is the realization of essentially a knowledge partner to help us work the left side of the system engineering V. So thank you. I hope you enjoyed this set of presentations. Hopefully this will be the beginning of a series of these. Again, here's some contact information. Please follow me on this channel, LinkedIn. You'll probably be seeing also posts around putting some of this information out on Substack as another way of getting my information out in a more textual format instead of the YouTube channel. But thank you all for joining, and I hope you enjoyed this presentation, the set of presentations.